Welcome to Study Loop.
We're going to be looking at the magnetic field of a sheet of current. But before we get to that, let's talk a little bit about current distributions or current densities. So when we write down current as just I, we're talking about an amount of charge that passes a particular point in a certain amount of time in coulombs per second. But what if that charge is smeared out over a two-dimensional surface or even throughout a three-dimensional volume? Then we talk about current density K is the amount of current per unit length. And that happens with a current sheet, which you can imagine made up of individual wires that are each carrying current. So over here, I have a current sheet, and you can imagine that the current sheet is divided into strips, each of which is carrying a current I, and the total current is I per unit length times whatever length that you are incorporating. Okay, and likewise, there is a three-dimensional current J, which is I per unit area. And the idea is that you have current going through individual pipes that make up a three-dimensional structure. But here, instead of breaking up that current sheet into individual wires, what we're really thinking about is that the sheet has a stationary charge, surface charge on it, and the whole sheet is moving. And it works the same way. Seriously, you have charges that are moving on a two-dimensional structure, and they are moving past a certain line over time. So K can be written simply as sigma times velocity. And if we want to give it a vector, the current is flowing in the direction of the velocity, depending on the sign of the current density. So it's moving with the velocity if you have positive charge. It's moving the opposite way if you have negative charge. So with that being said, what we're now going to do is look at the magnetic field of a current sheet. And we can imagine that sheet as made up of wires. It may be helpful to visualize that are all going in the same direction. So the K, or the velocity, is going into the page, we'll pretend. And what Ampere's law says is that the magnetic field going around a closed loop projected onto that path with a line integral is mu naught times the total enclosed current. Okay, so there's our sheet, and I can kind of imagine the edges of the sheet, but really Ampere's law works only if you have an infinite sheet. And now I want to use the right-hand rule to figure out which way my loop that encloses those little wires should go around. And so I'm going to put my thumb into the direction of the current, and then I see that my fingers wrap around in a clockwise direction. And this is similar to if you had a single wire. What you know is that the magnetic field would circulate around that wire in circles going in a clockwise fashion as well. What's different about the current sheet is adjacent wires are going to cancel the magnetic field on the sides. And so the only place that there's a magnetic field projected onto the loop is above and below. and it's going to be parallel to the loop. So we'll give that loop a distance L, and our projection of that magnetic field onto that loop is twice B times L is mu naught times the current enclosed. And here we're going to be using the linear density K times L. So imagine each of those carrying a current, and you have L of them. So what we can then propose is that the magnetic field, at least in its strength, is equal to mu naught times the density over 2. And we can replace our K with sigma B, magnitude, no vector needed for magnitude, divided by 2. And we would get our direction from the right-hand rule and the sign of the sigma. Okay, so you would use the right-hand rule in a similar fashion to wires. So here, let's say that the conveyor belt is going into the page. We would know that the magnetic field is pointing to the right above the plane. So for example, belt carrying positive charge, into page, into screen or page. B above the belt points to the right. And of course, the opposite direction underneath.